A sequence diagram is like a comic strip that shows who talks to whom and when. Imagine you are playing a game of catch. The ball goes from you to your friend, then back and maybe to a third player. The diagram draws each player as a vertical line, and the ball throws as arrows moving down the page. In software, we use it to picture how objects like a phone app, a server, or a database exchange messages during a scenario, such as logging in, buying a ticket, or sending an email. It helps developers understand the step-by-step flow, spot missing calls, and communicate the design to non-technical teammates. Additionally, sequence diagrams serve as a bridge between requirements and implementation. They expose hidden dependencies, clarify timing constraints, and can be transformed into test scripts, for example, using BDD style given when then. In agile environments, they are often created during story grooming to provide a quick visual contract that the team can validate before coding begins. Think of a sequence diagram as a stage with actors. Each actor or object gets a lifeline, which is a thin vertical line that starts at the top when the object is created and goes down as time passes. When one lifeline sends a message to another, we draw an arrow from the sender to the receiver. The arrow can be solid, a call that waits for a reply, or dashed, a signal that does not wait. While a lifeline is busy doing something, we put a thin rectangle called an activation bar on its line like a spotlight, showing that the actor is currently active. Additional syntax includes self-messages, arrow, looping back to the same lifeline, destruction, symbols and X at the bottom, and return messages, dashed lines. Together, lifelines, arrows, messages, and activation bars tell the story of who does what, and when making it easy to detect synchronous versus asynchronous calls, reentrancy, and potential race conditions. Control flow in a sequence diagram is similar to the difference between a phone call and a text message. A synchronous message is like a phone call. The caller stops, waits until the callee finishes and says hello back. In the diagram, this is drawn with a solid arrow and a return arrow. An asynchronous message is like sending a text. The sender keeps going without waiting for a reply, shown with a solid arrow but no return arrow or a dashed arrow. Timing marks can be added to show delays, like a pause symbol to say wait 5 seconds. UML also supports combined fragments such as alt, opt, loop, and par to model branching, optional paths, repetitions, and parallel execution. For example, a web page load may be modeled as an async HTTP request, no immediate return, followed by a parallel fragment that updates the UI while the response is pending. Timing constraints can be attached to messages to verify performance requirements. To turn a use case into a sequence diagram, start with the story written in plain language. User logs in, system checks credentials, then shows the dashboard. Identify the participants, dash the user, the login screen, the authentication service, and the dashboard. Write each step as a message. User to login screen, enter username / password, login screen to authentication service, verify, authentication service to login screen, success / failure, login screen to dashboard, display. Place the participants as lifelines in the order they appear, then draw the arrows exactly as the steps occur. This method guarantees that the diagram follows the original requirement and that no step is forgotten. Validation can be performed by tracing each requirement to a diagram fragment requirements to diagram traceability matrix, and by generating automated test cases from the message sequence, for example, using Cucumber step definitions. Design patterns are reusable solutions, and sequence diagrams can show them in action. For example, the observer pattern looks like a subject sending an update message to many observer objects. The diagram will have one lifeline with arrows to several observer lifelines. When you refactor code, you can redraw the sequence diagram to see the new flow. Perhaps a singleton object is now used, so all arrows that previously went to many instances now point to a single lifeline. Similarly, a strategy pattern will replace a family of conditional messages with a single call to a strategy interface. By comparing before and after diagrams, you can verify that the refactoring preserves behavior, that the number of messages does not unexpectedly increase, indicating possible performance regression, and that new responsibilities are correctly encapsulated. A state chart, also called a state machine diagram, is like a board game where each square is a state. and the dice rolls are events that move the piece to a new square via transitions. For a traffic light, the states are red, green, yellow. When the timer event time expired occurs, the machine moves from red to green, then green to yellow and back to red. The diagram draws circle states and arrows transitions labeled with the event that triggers them. States can have entry-exit actions, e.g. turn on/off a light, internal actions, and guard conditions. Composite states allow nesting, and orthogonal regions enable concurrency. State charts are ideal for modeling UI widgets, protocol handlers, and embedded controllers where an object's behavior depends on its current mode. Mathematically, a finite state machine is defined as a 5-tuple M equals S, E, delta, S sub 0, F, where S is a finite set of states, for example red, green, yellow. E is a finite set of events, for example timer emergency. Delta maps S cross E to S is the transition function that takes a current state and an event and returns the next state. S sub 0 is in S is the start state, for example red. F is a subset of S is the set of final or accepting states optional for many UI machines. For example, delta of red and timer equals green, delta of green and timer equals yellow, delta of yellow and timer equals red. This formalism lets us reason about the system using math proofs. Check determinism, each state event pair maps to at most one next state, compute reachable states, and generate exhaustive test suites by traversing the transition graph. Extensions such as Mealy and More machines incorporate output functions to model reactive systems. Sometimes an object needs to be in several places at once, just like a kitchen, where the oven can be heating while the timer runs. In state charts, we model this with orthogonal concurrent regions. A parent state is split into two side-by-side subcharts that progress independently. Hierarchical nested states let us group related states like a playing state that contains substates running and paused. Composite states combine both ideas. A music player might have a top-level on state that contains a concurrent region for playback, playing, or paused, and another region for battery, charging, or discharging. UML notation uses a thick border to denote a composite state and a double-line partition to separate orthogonal regions. This reduces diagram clutter, mirrors real-world layered behavior, and enables modular verification. For example, model checking each region separately. Choosing between a sequence diagram and a state chart depends on what you want to show. Use a sequence diagram when you care about the order of messages between many objects. For example, the steps of an online checkout, where the cart talks to the payment, gateway, inventory, and shipping service. Use a state chart when you want to describe the life of a single object, like how a user account moves from new to active to suspended based on events. Criteria include scope of interaction, multiple participants to sequence, single participant lifecycle to state chart. Temporal granularity, detailed step-by-step flow to sequence, high-level mode changes to state chart. Complexity management, many parallel message flows are harder to capture in a state chart. Concurrent states are easier in a state chart. Often both are needed. A state chart defines permissible states and triggers, while sequence diagrams illustrate how external objects invoke those triggers. Aligning both ensures consistency between interaction design and internal behavior models.